So for this question, we need to calculate the vertical deflection beneath the applied node. That means we need to know the deflection at this point. So this beam is fixed support. If we say this is fixed support A, and we have a hinge on the beam. If we say this is point B, and at the point C we have a concentric node P. So at point D is a roller support. So this is the beam, and we want to calculate the deflection. So here we want to using the method of virtual work. So a method of virtual work, first of all, we need to calculate the internal bending moments for the real systems. So here, the question already give you the bending moment here. So the bending moment is at the point A is negative PL over 2, and then linear change over at point C is PL over 2. It's PL over 2. And then change to 0 at point D. So this is for the real systems. So although this question gave you the bending moment, but we can easily derive this bending moment. So how can we do that? So first of all, we do analysis on the beam segment BD. So this B, D, and C. So at C we have a concentric node. So at the point D, we have a reaction force. Well, at the point B, we have a reaction force. So we can easily derive the reaction force at the point D is P over 2. The reaction force at point B is P over 2. So after we know the reaction force at the point B, then we know this point A, this point B. We know at point B we have a force over here is P over 2. Then we can draw the bending moment as shown on this diagram. So we skipped these steps. You can derive the bending moment by yourself. So now we have the internal bending moment for real systems. And this is for real system. And for the virtual systems, we apply a load unit node at point C. So this bending moment is same with this shape, because if we apply node P, the bending moment is the shape is like this. If we apply the unit node 1, the bending moment diagram will be same shape. Okay, so here is L over 2, here is L over 2. So this is negative, this is positive. So we have points A, B, C, D. Okay, so once we know the internal bending moment for the real systems and the internal bending moment for the virtual system, this is virtual system, then we can derive the deflection at the point C equal to the small m, capital M over EI dx. Okay, the small m is a virtual internal bending moment. The capital M is the real internal bending moment. So showing on these two diagrams. So because the coordination systems is the coordinates is set up like this. This is y, this is x. So from 0 to 3L. So we can write down here is 0 to 3L. So, but look at these coordination systems. It's not easy to come out the function expression for this curve. So now I would like to build up a new new functions for the bending moment. So what I got to do, I build up a new system here. So first of all, I build a new coordination systems. If you see this y1, so this is x1. Okay, I build up here y1, x1. Okay, so then we can express this curve. This curve, if I say, is m1. So m1 can easily derive. M1 is equal to p over 2 x1. So this is the function expression for this curve m1. And for this curve for here, so if we say is small m1, the small m1 is easily derived is 1 over 2 x1. Okay, after we got m1 and small m1, then we need to derive the function here. So this we say capital M2, this is say small m2. Okay, for small m2 and capital M2, I would like to build up a new coordination systems. It's like this. Okay, it's y2 x2. Okay, so this curve is go through this orange point. So we can also easily write down m2 is equal to negative p over 2 x2. m2 is equal to negative 1 over 2 x2. So after we got the expression m1, capital M1, small m1, capital M2, small m2, then we can evaluate these integrals. So we go to here. So that delta c can be expressed by two integrals. First of all is for the y1, x1 coordinate system is changed from negative L to L. From A to C is negative L to L. So we have m1 is 1 over 2 x1 times capital M1 p over 2 x1 times ei dx1. Okay, this is first part. The second part is the coordination systems at y2 x2. So it's changed from negative L to 0. Okay, so small m1 is negative 1 over 2 x2, capital M2 is negative p over 2 x2 1 over ei dx2. Okay, so we can very easy to derive the integrals. So it's here's 1, it will be 1 over ei, and is 12p x1 cubed negative L. Okay, so if plus same over here is 12p x2 cubed negative L to 0. Okay, if we evaluate these two terms, we can get out the result is 4ei p L cubed. Okay, so this is the method of virtual work. So we evaluated the two integrals. Okay, so as we know, we also learned use visual integration to solve the integrals. So for visual integration, what are we going to do? So visual integration, we need to find, we have three shapes on each diagram. So at here, so we have this shape apply to this shape. We have this shape to these triangles. We have this one to this one. Okay, so if we go through the table for visual integration, you will find, okay, if we have the one triangle shape and the m1 with the other triangle shape with m3. Okay, is that so? If our bending moment diagram shape is both a triangle like this, then the integral will be, we can easily derive integral is 1 over 3 m1 m3 L. Okay, and for the shape like this, okay, m1 L shape like this, it's also the integral is 1 over 3 m1 m3 L. Okay, so once we got the bending moment diagram, real bending moment diagram, virtual bending moment diagram, we don't need to calculate the expression for the m1, capital M1 or small m1. We just, based on the shape, we can derive the integrals. Okay, we can find all these. So this one, this one, this one, these two, this pair can all related to this. One pair like this, the other pair is like this. Okay, so then in total, the deflection is equal to 3 pair. For each pair, the expression can be by m1, m3. Okay, m1 we can find is L over 2. M3 we can find is PL over 2. Okay, times L. Okay, we cancel, so then we times 1 over EI. Okay, so this is the integral, this is the 1 over EI. So we cancel 3, then we got 4EI PL cubed. Okay, so this is the method of virtual work to solve these questions. First of all, we get the expression for the m1, m2, small m1, small m2. Then we do the integral. Then we evaluate the integrals. So the expression part is that we define 2 new coordination systems to help us to find a simplified function for m1, m2, small m1, small m2. Okay, to help us easily to solve the integrals. Also, we're using the visual integration to find the pair of 2 bending moment diagrams, and then we can easily derive the evaluate the integrals for the visual work method. Okay, so this is the method of virtual work applied to these questions. Thank you.